Hello, my name is Gabrielle Taylor. I'm going to be doing homework 2, part A. We're going to be doing the first one. So it says using the energy balance to derive a algebraic expression for calculating the thermal diffusion through a uniform bar, assuming there's a constant thermal diffusivity, differencing via explicit differencing of the temperature gradient. And so a little more about that, the bar is we have an initial steady state, and then we are going to be heating it on both ends to different temperatures. On the right side, we're going to do 80. On the left side, we're going to do 50 degrees Celsius, and then they're going to be at a steady state, right? So let's go to our, let's draw this out, right? So we have a bar. And so we're going to just discretize this. That means we're going to split it up into sections that are equal distance, right? So they have an equal width. Right. And then this bar pretty much has an area of it, right? It's not flat. So it has this cross-sectional area. And each of these pieces has a width of delta x, right? And they're all delta x. So, we know that we have a constant thermal diffusivity, which is this. So that's constant. So that is pretty much going to tell us how the temperature propagates through the bar, right? So how the temperature is going to move through this bar. And so we want to figure out is how the temperature through this bar changes. But we're going to first do it how it changes, and then we're going to next do it how it changes over time. But let's just look how it changes, right? So we have a bar here, and this is TJ, right? So this is, we'll just say this is a temperature of this particular slice of piece at position J. And so after this bar piece, we're going to have TJ plus 1. So this is the T before it, position before it. And then we have a position TJ minus 1. So that's a position after it, right? So we're going to be making a differential equation of this, and it's going to be based off of how that temperature changes, right? So let's do this. The partial derivative of TJ, partial derivative of time, right? Because this is going to be changing due to time, in respect to time. So we want this to equal heat, right? Because this is all about heat flow. So what do we know about Q? Q is going to be joules per second. So this here is going to give us Kelvin per second, right? Because it's temperature over time. And so we can multiply this by our heat capacity, and that's going to give us joules over grams per Kelvin. So we're going to cancel out our Kelvin, and we need to cancel out our grams, right? So we can get to the units of joules per second. So what we're going to do is we can multiply this, since we have an area and stuff like that. We can do our rho times RV. That will give us our grams, so we can cancel that out, right? So we're going to have joules per second. And that's going to equal our Q. So we don't have a volume of this, but we do have we have a cross-sectional area, and we do have a standard of our width, right? So that width is never going to change, and that area is never going to change. So we can use this, and it won't be changing due to time as well. So we're going to have is our rho times our delta x over our area. I'm just going to keep it as area because we don't have any other areas. Then our heat capacity over the partial derivative of TJ over the partial derivative of time. So next we have is we want to figure out what our Q is. So we have Fourier's law. Fourier's law tells us that Q is going to be equal to the negative thermal conductivity times our area times dt, the temperature, the change in temperature over the change in time, right? So we can just plug that in to this. Okay, so what do we know about both of these is we have an area. We can cancel that out to make this simpler. So now we want to really focus on this part here. So let's focus on that. So with this, we can see that we're changing due to temperature and time. All right. So if we think about this bar, the bar's temperature is changing in respect. So this is changing, right? If we think about it, we are starting at a steady state, right? This is going to be 20 degrees Celsius in the middle. Like if we pick the middle, it's at 20 degrees Celsius, and then at the edges, it's heating up. So the temperature is moving in between, right? The temperature is going to be moving to the middle, right? And so we have 80 degrees here, and we have 50 degrees here. So the temperature is going to be moving inward, right? And so what is going to be affecting TJ here is going to be these two slivers. Those two pieces are going to be affecting the piece next to it because it's how the temperature propagates through the bar itself, right? So if we're wondering how that temperature is going to change due to time, it's going to be based off of what is touching that sliver, what is touching that piece that we're looking at, particular, which is TJ. We're not looking at anything else. So we can write this as, I'm going to rewrite this. We took out the area. Okay. So we have, if we do TJ, let's do the first one. So TJ plus 1, right, is going to be affected by TJ. And that's going to be our heat. So we have to subtract it. And then if we have it like this and this, these two center pieces, it's going to give us our delta X. And they're all going to be delta X. They're all going to have the same width, right? So delta X plus TJ minus 1 minus TJ over delta X, right? Because higher heat is going to move to lower heat, to something that has a lower amount of heat, right? It's all about an energy flow. So they are all going to be giving heat to TJ, pretty much. So after this, let's look at this. So what we can do next is we know that the thermal diffusivity has an equation of, so it is going to be K over QC. Well, rho. Rho's this. Sorry. I've been writing it as Q. It's rho. So just know that this is rho. I got it flipped. Okay, sorry. Rho. So that's her density. So it's going to be the thermal conductivity divided by rho times our heat capacity is going to be our thermal diffusivity. So we can pull this and divide this so we can cancel, and we can pull this on this side so that we have it kind of simpler, right? So we can rewrite this to what we have, and also we can combine these because they have similar denominators, so we can do that as well. So we'll have is delta X over Q over the thermal conductivity, and then we'll have our partial derivative of TJ over partial derivative of time. So next, what we're going to have is, it's going to be T is going to be TJ plus 1 minus 2TJ plus 2TJ minus 1 all over this. So that's just combining those like terms together. Next thing that we want to do with this is, let's look at this, right? We want to look at this part now. So we want to do an algebraic expression of this. And what we were saying is that we want this to be a temperature gradient, right? We want to know how the temperature propagates through the bar, but we also want to know how the temperature propagates through the bar over time. So the temperature of this, so we're wanting to know how the TJ changes, right? And we want to know how it changes due to time. So this is going to change over time, right? So we want to change this too. So partial derivative of Tj over the partial derivative of T. And this is going to change. So we have Tj n plus 1. So Tj in the time after, so the time step after it, minus Tj, because this is going to be how that temperature changes over our delta T, so over our change in time. So we're going to plug this back in, and then we're going to solve for this, because we want to know, again, how Tj is changing over time, right? So we're going to solve for this. And so yeah, let's do that. So let's plug it in. I'm just going to go to the next page. So we have our delta X over our thermal diffusivity times, and we're going to have is Tj n plus 1 minus Tj n, and then we're going to have that as a T. I'm going to make this smaller. Okay. We'll make that smaller. So, next thing is we have our Tj. So, plus 1. Now these I'm going to keep as an n because this is the current time step that we're doing, right? Then minus 2 Tj n plus 2Gj minus 1 n over our delta X. So we can combine like terms of our x's if we just pull that over. So it's going to be x squared over this, and we can also pull from this here, just pull that out. So we have this. Then we have this as Tj n plus 1 minus Tj n is equal to Tj1 n minus 2 Tj n plus 2j minus 1 n. Okay, so we're going to multiply, we're going to divide this, so it's going to flip that, right? And then we're just going to add this part here, and then we'll be able to get Tj n plus 1. So it's going to be Tj plus 1 is equal to Tj n plus thermal diffusivity times our change in temperature, change in time over x squared, Tj, 2Tj, and Tj. Tj minus 1 n. Okay. So now we have that. We have this equation here. And this is going to help us with our coding portion of this. So we'll go to that part. We'll be doing part A2. So what it says is we're going to simulate a time-dependent response using the uniform bar initially at 20 degrees Celsius. So that's going to be at steady state. And we're going, after it ends, it's raised to maintain 50 and 80. So it's going on the right, on the left, it's going to be 50 degrees at that end, is going to be added at 50, and then the 80 on the left, on the right, is going to be 80 degrees Celsius, respectively. Then we're going to discretize the bar into 100 sections, and we're going to show the simulated response for R is equal to 0.499, and R is equal to 0.503. Okay. So let's look at this. So we have all this stuff in here, and what we wanted to add to this is, let's do our alpha. Alpha is going to be 1, and then we have is our dt is going to be 0.1, and our dt is going to be pretty much how is the length of our time step. So it's going to be 0.1, and then dx is that, how much is that width of that bar, is 0.5. And then we have, after that, is we know we're going to discretize the bar into 100 sections. So that's going to be n 100. So this means how many pieces are going to be split up into. And then also we can do is we have our R. We know what our R is because we already derived that. So that was going to be alpha times our dt divided by our dx squared. Okay, so after this, what we're going to do is we need to make kind of an array of our temperature profiles, right? We know that this has 100 sections, and we're starting at a steady state of 20, right? So all these pieces are at 20. So we can do is T is equal to np dot full. So we want our 100 pieces, which is our n, and we want to fill those up with 20. Okay, and I can show you what that looks like. So here we have 100, fills up to 20 pretty much. Okay, next thing that we want to do is we have our first data point. So on the left, it's going to be added to 50, so we do 50. And then t is equal to -1. So in Python, if you do -1, it goes from that point that's in the front, and then it hits it back one space. So that's one space is going to be this little piece right here. So we have here, that's 80. So we run that again, it changes that. Okay. So after this, what we're going to do is, I think that's good. I'm just going to delete this. So now we want to use our equation that we already had, that we made, right? So we had t, so our first one was tj n plus 1. Now we're not going to worry about the n plus 1 yet. We're just going to be worrying about looking at the positions that they're currently in. So that's going to be 1, -1 is equal to, right? So that's tj. And then we have tj, which is going to be 1, -1. So tj is pretty much, if you do 1, -1, that's going to be doing all the places except for the first one and the last one. So it's going to be taking out that 15 to 80. So it's going to be all the values in between of that. So then we have plus, and then we have r times, right? And let's do, so it's tj, right? This one is going to be tj plus 1. So tj plus 1, we want to do is we want to not account for the last two values. So -2, we'll stop accounting for those. Minus 2 times t, and then that's tj, so it's 1, -1. Plus, and then we have tj minus 1, tj minus 1. So that's going to be, we don't want to account for the first two. So it's t, and then 2, like that. Okay, so now we have our equation. So we want this to be a time graph, right? So this is going to be due to some time. So let's do a for loop. So for I in a range, let's do 100. And then, okay, so you have that, right? So this is pretty just going to overwrite all those t's, right? But what we want to do is we want to have a temperature gradient. We want to know how the temperature propagates through the bar, right? So we need to save all those values so when we have a graph, it shows kind of a line. So it shows how that temperature progresses through that bar. So we have to save those values, so we can do this. So this is going to be our temperature profile. So profile, and it's going to equal, like this, and you can do t dot copy. Like that. Okay. And then you can go down here, and so then you do t profile. So t underscore profile dot append, and then we're going to do t dot copy. Copy to like that. Okay, so that's that's going to give us a copy of every time it goes through that iteration, and that iteration is our time step. So we save that, and then let's make our graphs. So fig is equal to make underscore subplots, plots, and then after that, what we can do is this. So we could do our k, so for k, for k, and we wanted to use k for our copy. It's 4k. Is it range? So for K and profile, so we have that, and then let's do fig dot add underscore scatter. Let's do mp dot append, and we're going to do n, so it's going to give us, is that how you spell it? Maybe it's, no, it's that. Maybe. Okay. And then y is equal to our k. Okay. So this should give us append, should give us n, which is going to give us 100 spaces, and then our k is going to be based off of that temperature profile we have here. And then we can just do fig underscore show. Let's see what that does. Maybe this P here. That is bad. No. Not append, it's what's it called? Okay, so it's not append, it's arrange. Okay, there it goes. So, so you can see our graph here. So we have a lot of lines because we have a lot of time steps. This is going to tell us all the time steps, and this is our two temperatures here. So you can see that we're not at steady state yet. So we're going to have to increase our time steps because this isn't enough time for the bar to reach steady state. Right? So if we go to 1,000, and then if we want to cut down the amount of lines we have here, I mean, let's just try it. No, I have to do this. There you go. Let's see. This might be run slow because I need to do it wrong. Okay, so it's still not flat. So we go here. Let's do 200. There you go. I know this is 200. I'll get more of them when we add the time graph. But this isn't completely flat. We can see that it's still kind of bowing here. So let's add another time step. Let's do 10,000 and 200 here. So now we are completely flat. So we're going to steady state, and you can kind of see how it's going up and stuff like that. So the next part of it was to change R, right? So if we change this R, right, So pretty much what it has is we have the Newman stability, and Newman stability tells us that R, if it's not equal to 0.5, if it's bigger than 0.5 pretty much, that we will have a lot of instability. So let's do 0.499. Okay. Let's look at our graph. It looks very similar. You know what I mean? It's very flat. It's going to steady state, right? So let's change this to 0.53, right? So we're only moving very little. Let's look. Okay. So you can see there's a lot of instability with this, right? Yeah, we're getting a lot of instability. But let's look at over here. So this is temperature on the side. So it's going to go to 2 to 10 to the 47th degrees Celsius, which is extremely high temperature-wise. So we can see that if R is above 0.5, you're going to have crazy instability, that it's going to reach very high temperatures. So we are going to derive pretty much why this is, looking at that R factor, right? So we are going to be doing the von Neumann stability so that we understand why our R factor is going to be less than or equal to 0.5. So I have our original equation we derived for this, and so let's get into it. So the first thing that we want to talk about on this one is, let's write an equation for this. So let's write down our equation. Our equation is dt over, well, it's the partial derivative, right? So it's going to be that dt over d time, right, is going to be equal to delta, which again, delta is going to be our thermal diffusivity. And then it's going to be dt over second derivative of dt, the temperature over the change in x, right? So on the second. So the answer to this is T is e to the negative, sorry, let me write that alpha better. So it's negative alpha k squared delta, sorry, just T. This is just going to be T. Sorry, T. T is in time, not temperature. And then e to the ikx. So we have that. So we need to understand and kind of look at why we think that T is this, why we think this here is the answer to this. So let's do the derivative of this equation, of this T, pretty much. And so when you do a derivative of something that to the e, you bring down the constant of that, of the factor that has the thing you are deriving it by. So if we're doing T with time, so if we're doing dt, temperature over d time, you're going to be only looking at the time one, and you'll be keeping the same factor as that, right? So with that, let's look at this. So dt over dt is equal to this one. So you bring down it, so it's this, k squared e negative kt, right? And then e ikx, right? Because these are you're gonna keep what's there, you're only going to derive on that. This is the time factor. Okay. So what we know is this here is t here, so we can just plug that in again. So dt is equal to negative alpha k squared and then that's going to be equal to t. So let's do dt dx, right? So that's going to be the next one. So we're going to have is ik is e to the alpha kt e to the ikx, right? And that's also going to be giving us t again. So dt dx is going to be equal to ikt. And then if we do the second derivative of this, that's going to be equal to I squared k squared t. So let's plug into this equation here, and let's see if this is the correct answer, if this makes sense. So we have is dt. So I'm just going to kind of make a block out here, block this off real quick. So it's going to be negative alpha k squared t is equal to alpha I squared k squared t. Okay, so one thing about I is going to be equal to the negative square root of 1. If we do the square root of this and the square root of that, that will cancel out that square root, so we'll just have negative 1. So that is just going to be negative. So we'll have is eventually is alpha k squared t is equal to negative alpha k squared t. So this is the correct solution. So now what we want to do is we want to plug it back into here, right? And we want to figure out that r, right? And figure out those limits of the r. So we want to find is tj n. So we have to use this t function that solves it. We need to use that and do it in a time and step variable. So let's do it over here. So we have tjn. So we're going to be using like very similar, but we're just going to add the time steps and the movement steps as well. So the j. So we have is e to the negative alpha k squared, and this is in time. So time with that is n, right? We have time is n, and that's going to be the change in t. And then we have e, which is going to be ik, and then we have that's x. So that would be j, because j is related to the changing in position, delta x, right? So now what we want to do is tj1n. So e negative, so ek, so this first one's probably, it's going to stay the same, not changing in time step, or only changing in position. So j plus 1 x. Okay, and so we can distribute out this here. So this is going to give us tj1n is equal to e negative alpha k squared n delta t e. We want to have ikj delta x, and then we're going to have eik delta x. Okay, so we can see here, this is this here, right? So we can just plug that back in. So we'll have is tj plus 1n is equal to tjn, and then what we have left is right here, so eik change in x, right? So this is going to be our equation for this right now, for tj1 plus n. Okay? tj plus 1n. So if we do tj, if we do tj minus 1n is equal to this, right? That's just going to flip the sign because this is just going to be changed to a negative. So it's going to be tjn negative ik delta x. Okay. So we're going to plug this into here, right? We're going to plug that back in based off of what we had and solve for it. So we have tj n plus 1 is equal to tjn is equal to plus r So the first thing that we have is we're going to keep this all in TJN. So we have the first one is TJ plus 1, so TJN I e to the ik delta x minus 2TJN, and then plus TJN e to the negative ik delta x. Okay, and that's in parentheses. So we can pull out a TJ because all of them have TJ in them. TJN, sorry. So from that we have TJN is equal to 1 times R, and then we have eik delta x minus 2 plus e negative ik delta x, right? So, and then from this, what we want to do is we can look at the Euler's solution. So that's going to be x is equal to cosine of x plus negative that, right? So, since we know this here, this is a solution, we know that we can plug this into here. So if we have the first one, let's see the ix delta x, the ik delta x, e to the ik delta x. So cosine is going to change to k delta x plus I sine of k delta x. And then if we did this to e to the negative ik delta x, we're going to have is cosine of k delta x, but it's going to be minus I sine of k delta x. So these two cancel out, right? So you're going to cancel out all the i's of this. So now we're going from not imaginary. So we're going to have real numbers after this right now. So now we're going to try to figure out a function. So this is due to r, and r is going to be multiplied by the TJN. So we have is 1, well, I'll just rewrite this first. So I'm only going to be looking at the I plus r times, so we have 2 of the same thing. So it's 2 cosine of k delta x minus 2. Okay, and then this is to the negative 1, negative here. So we move over the, we're going to be subtracting by negative 1, by subtracting by 1 on both sides. So this is going to be 2 r 2 cosine of k delta x minus 2. And then we'll have 0 on the side. Okay, so what we know from cosine is that the biggest cosine can get is negative 1 or 1. And so if we plug in 1 to this, we will get a 0, because 1 times 2, 2 minus 2 is 0. So that will be specifying that 0 here. So let's do negative 1. So if we do negative 1, we'll get r is negative 1 will be negative 2, 2, there, 0, negative 2. Right, so that will be r is equal to negative 4. Okay, and then if we divide by negative 4, that switches the sign, right? So then we'll get 1/2 is, so it's saying that r is either greater than or is r is less than or equal to 1/2. So this is why r, when we are doing the function, the coding, why there was no stability with that r when it was greater than 1/2 or greater than 0.5. So this is why that works out that way. So that is the end of part A.